All right, the skier problem. So the velocity, we have a skier that's starting from rest at the top of the ski run. She accelerates at a rate of 3 meters per second squared for 15 seconds, wildly out of control. After the 15-second acceleration, she immediately plows into a 12-foot high snowdrift directly in her path. Watch the video if you want to see it. And stops in only 0.11 seconds. First thing we're going to do is sketch a VT graph of the motion. The red dashed line is representing where the skier hits the snowdrift. So we click on our graph and then click Edit. That allows us to get into the drawing window. And then we're going to create a line on here. And it'll take it a second before it is happy. Once you get the plus sign that doesn't have arrows, you know you can draw. Our skier starts from rest. So they're going to be starting at 0, but then they're going to get faster. So our skier's motion down the hill is going to look something like this. And you can change the color if you want to. You can change the thickness. I'm going to do that just so it shows up a little bit better. And then now that she's going this super fast, she's going to hit the snowdrift and then come to a stop. So she's going to start at this speed and then slow down really fast. And so we've got a big deceleration rate here, big negative acceleration, big positive acceleration over here, but not as big as this one here. So our acceleration going down the hill, so getting faster and faster and faster, and then coming to a sudden stop in a very short amount of time. We hit save and close, and that gets us done with our graph drawing. This is the time of the year where we start doing diagrams to support our work, because so much of what we do describes a reality, a physical reality, that drawing a picture really, really helps. So here we've got our skier going down a hill, and then they're going to plow into a snowdrift, and it looks just like the video, other than it's not a gator in the video. And what we're going to do is label the givens that we know. So again, we click on our diagram and click Edit. And our givens, it'll take it a second before it allows you to edit. Once you get a cursor, you can start writing. We know our skier starts from rest, so VI equals 0. They tell us in the problem that the acceleration is 3 meters per second squared. And we also know that she does this for 15 seconds. To get a squared, formatting-wise, that's a control period. And if it stays up in that superscript mode, you can hit control period again, and it will make it unbe a subscript or superscript. So then the givens for the stopping part, we know that she's going to come to a stop. So VF is going to be equal to 0. So VF is 0 at the end. And we know that it takes her only 0.11 seconds in order to come to a stop. And that's all I know at this point. So we save and close, and now those are labeled on our diagram. So now we're going to do some problems. So what is her final speed after 15 seconds of acceleration? So we start with the givens. Remember that those need equal signs. VI is equal to 0. The acceleration is equal to 3 meters per second squared. I'm going to do my superscripts later. T is equal to 15 seconds, and we are looking for the final. So we need an equation that'll help us find V final. We've got 2 of those. So if we go into the equation sheet, and remember, I like the second page more than the first page because it divides it out by what we're solving for. So the velocity, VF, excuse me, the VF, we have AT plus VI. That's one of the VF equations that we have. And we have VF is equal to the square root of 2AD plus VI squared. I don't know D, so this equation isn't going to work because I don't have all the pieces that I need in order to calculate it. But I do have A, and I have T, and I have VI. So this equation is going to be great. So VF equals AT plus VI is the one that I want to use. So the next step is to write that equation, and we do it just in terms of letters. And now we're going to do the substitution. So VF is equal to, our acceleration was 3, so everywhere we have an A, we put a 3. Our time is 15, and the initial is 0. So we can plug that into a calculator, but this one I can actually do in my head. So 3 times 15 plus 0 is 45 meters per second. So that's our first one. The next one is, what distance does she travel during the entire 15 seconds? So our givens are basically the same. So I'm going to copy and paste them. Now I know what my V final is, so I can include that one here. And I'm looking for distance. So we go back to our equation sheet to look for an equation that solves for distance. I can't use this top one, v equals dt, because I have acceleration. Since it's accelerating, this equation does not work for us, so we can't use that one. But the second equation actually does. So we could do 1/2 at squared plus vit, because we have a, we have t, we have vi. It's all good. We could also use this bottom equation here, that we have v final squared minus v initial squared over 2a. That works for us as well. So it really comes down to, which one do you prefer? I think it's going to be easier for me to write this one, so this is the one I'm going to choose. D is equal to 1/2 a t squared. I'm going to do the subscript in a second. Vi t. Now I'm going to do my substitution. Whenever I have a half, I do 0.5 because it's easier to type that into a calculator. My acceleration is 3, my time is 15, and I'm going to be squaring that. So it's 15 squared, and then plus my vi is 0, and the t is 15. So this one I can't do in my head. I'm going to need a calculator. So whatever calculator it is that you're using, get that. I'm going to use the Desmos calculator. So it's a Desmos scientific calculator. I think it's really a pretty good one as an online calculator goes. You can also very definitely use a real calculator. Real calculators are good. Okay, so when we do this, so I'm going to clear everything out of here. I have 0.5 times 3 times 15, and I need to make that squared, so I'm going to go ahead and hit the squared button, so it says a squared over here, plus, and then 0 times 15. Now I don't really need to add in this part because 0 times 15 is just 0. So if I don't put that into my calculator, I'm still going to get the same answer, and it's okay to not put that in. My answer is 337.5. So D equals 337.5. Now I'm going to round that to 2 digits. I'm going to keep the 3. I'm going to look at the 3 that's next to it and decide if it stays a 3 or if it goes up to a 4. I think it has to go up to a 4 because what's next to it is bigger than 5. So I've got a 7 here that's going to make that go to a 4, and I need to add a 0 to keep it the same size. So it was about 340. Now it's about 340. What is her final speed after 15.11 seconds? It's 0. She stops. So after she goes down the hill for the 15 seconds and then goes into the snowdrift for 0.11 seconds, she stops. Now number 6, this is the key. This is why we love this problem. So figuring out her initial speed going into the snowdrift. So we're going to go back up into our diagram here, and we're going to label some stuff. We now know that her V final, after she goes down the hill, is 45 meters per second because we figured that out in part A. So she starts at 0, she speeds up, she gets faster and faster and faster and faster, and then right here, she's going 45 meters per second. Now she goes into the snowdrift. That means her speed when she goes into the snowdrift is 45 meters per second. But that's no longer a VF. In the snowdrift part, that's her starting speed. So the VF that she had going down the hill becomes a VI going into the snowdrift. That can happen. You can actually change whether it's an initial speed or a final speed depending on which part of the problem you're looking at. So the V final at the bottom of the hill is the V initial going into the snowdrift. She starts at 0, goes to 45, goes from 45 to 0. And so it's the context that tells us whether it's a VI or a VF. So now let's take a look at our graph. We're speeding up. We start at 0. We go to 45 meters per second. So that's the snowdrift right there. She starts at 45 and goes to 0. So two different ways of looking at the same thing. So we're in the home stretch. So the VI Okay, so the VI of the snowdrift will be equal to the VF of the downhill part of the problem. She gets to the bottom of the hill with 45 meters per second, so she starts into the snowdrift motion with the speed she ended up with on the downhill part, which is 45 meters per second. So now let's figure out the rate of acceleration through the snowdrift. This is the money question. So our VI is equal to 45 meters per second for this part. Our VF is equal to 0. The time in the snowdrift is 0.11 seconds. We are looking for the acceleration rate. Let's go back to our equation sheet. We're looking for acceleration. We've got A equals V final minus V initial over T. I think we're good. We have V final, we have V initial, we have T. This equation is going to work for us. I don't think we need to look any further. So our acceleration is equal to VF minus VI divided by T. Okay, is equal to. Now notice here that it's not biggest number minus smallest number. It's V final minus V initial. Our V final is 0. Our V initial is 45. And then our time is 0.11. So when we plug that into our calculator, whoops, that's not our calculator. So when we plug this into our calculator, we're going to have 0. And actually, I'm going to back up because I would like to put parentheses on that. 0 minus 45, so final speed minus initial speed, and then divided by, so whole thing divided by 0.11 seconds. That gives me a negative 409, etc. And that's my acceleration. So negative 409.0909, etc. I'm going to round that to 2 digits. That's going to give me negative 410 meters. It's negative because it's slowing down. So we're going from a faster speed to a slower speed. So that should make sense. And it's meters per second squared. The last question was, what is the distance she travels through the snowdrift while stopping? So I'm going to go ahead and copy that. We now know our acceleration is a negative 410 meters per second squared. And we are looking for distance. So what equation should we use for distance? Let's go back to our equation sheet. We can't use this one. There is acceleration, so this one does not work. D equals 1/2 AT squared plus VIT. We have all those things, so that would be totally cool. We could absolutely use 1/2 AT squared plus VIT. And this one actually works because we have V final, we have V initial, and we have A. So we could absolutely plug into that as well. So depends on which one you want to do. I am going to do this first one because then I can copy paste and I don't need to write a whole new equation. So since we use that equation up here, I'm going to copy it and paste it. When I substitute in, I use 0.5 for the 1/2. The acceleration, the negative sign is important, so we need to include that. Our t is going to be 0.11, and we will be squaring that. And it's only the t that's squared. My vi, for maybe the first time, is not equal to 0. It's equal to 45, so we absolutely need to have that term in there. And I'm going to stick that 0 in there to make the decimal point more obvious. So we have 0.5 times negative 410 times 0.11 squared plus 45 times 0.11. So that was 1/2 a, so there's my a, my t, there's my t, and that's squared. My vi, so that's the 45, and then t again. So a lot of people miss that last t, but that last t is important. So times 0.11. So let's go to our calculator again, plug all that stuff in. We've got 0.5 times, our acceleration was a negative 410 times 0.11 squared plus 45 times 0.11. And our answer that pops up here is 2.4695. And that is distance. So now let's round that to 2 digits. B is equal to 2.5 meters. Now hopefully that makes sense, that she's decelerating, she's slowing down really, really rapidly. So she doesn't travel particularly far into the snowbank. It's a pretty small distance because that acceleration is really huge. So that's the skier problem. We use this a lot. And again, it's because of the step 6 where the speed changes going from one part into another.